Okay, so we're going to continue our discussion of the normal random variable, the normal probability distribution. Now, the normal random variable, being able to calculate normal probabilities, is probably the one single most important skill that you can develop if your ultimate goal is to do well in this class. Hopefully that is your goal. And if it is, then you need to learn to do this, and you need to learn to do it well. Now, thankfully, not only is it important, it's very, very amenable to drill type practice. That is, there's lots of problems in your textbook that you can practice on, and I want you to practice on those problems. I want you to do problem after problem after problem after problem. I want you to keep doing problems until you feel like vomiting, and then I want you to just go ahead and vomit, and then I want you to do some more. That is, I want you to work until you feel sick and nauseous, and then push and keep going. I want you to learn this stuff not just well, I want you to learn it so well. There's going to be multiple questions, lots of questions on your test. There's going to be multiple questions, lots of questions on your final. And in addition to that, the more complex material, which we're starting to zero in on, to understand that, you need to understand this. And so what I really want you to do, the ultimate goal, is not only to do this, but to do it effortlessly, to do it as if it's second nature. The ultimate goal is to be able to do these types of problems without even thinking about it, because that's going to make it that much easier to learn the material that's coming afterwards, the more complicated, more complex material, which is just waiting for us on the horizon. So, there are essentially three types of problems that we can be asked when x is a normal random variable. The first type of problem is, what's the probability that x is between two numbers a and b? The second type of the problem is, what's the probability that x is less than or equal to some number a? The third type of problem is, what's the probability that x is greater than or equal to b? Only three types of problems we can be asked. Now, the first one we've already done an example of with our walruses. So let's look at examples of the second and third type of problem. So, probability that x is less than or equal to some number a. For example, we might be asked, what's the probability that a walrus weighs less than or equal to 2,600 pounds? Which is essentially the same as asking, what's the probability that x, the weight of a walrus, is less than or equal to 2,600? Ah, my best friend, Appia Buff. So, here's my picture, my normal distribution, the mean's at 3,000. So 2,600 is somewhere to the left of it, right? It's less than 3,000. Right? So I'm just putting it somewhere to the left. I mean, it's somewhat arbitrary. I didn't pull a ruler out or anything. And I put 2,600. We want everything less than or equal to 2,600. So we want all the area that's less than that. We want all the area to the left of 2,600. Now, how can we find this probability? Well, we use normal CDF to always find normal probabilities, right? Normal CDF, LUMS, Lahore University of Managerial Sciences. Not a lot of people know this, but right, Lahore University of Managerial Sciences has won more NCAA men's basketball tournaments than any other college. Yeah, seldom known fact. So for this, right, the upper bound is fairly obvious, right? The upper bound is the rightmost bound. That area is very clearly bounded to the right by the number 2,600. The mean is 3,000. The standard deviation is 250. The only number that's maybe a little bit unclear to us, is what should be the lower or the leftmost bound. Because in this example, in theory, there really is no leftmost bound, right? That area just sort of trickles off towards infinity, right? Towards negative infinity, towards the leftmost tail. Now, in theory, ideally, we would just put negative infinity into our calculator, but our calculator does not have an infinity button. So we put sort of the largest negative number that our calculator can handle. and that is -1. So the negative thing, to put a negative number in your calculator, that's to the lower right-hand corner. It's actually just a little bit to the left and below the Enter key. So it's in the lower right-hand corner. So you would hit the negative sign. That creates a negative number. You would hit 1. Then you got to do the E. To do the E, you're going to hit the second function button and then the comma button. That will actually create the E, and then you go 99. So remember, what is that doing? Remember, e to the 99, e to the positive 99, says take the number to the left of it, which is the -1, and add to it 99 zeros. So again, that's an astronomically large negative number, quote, large negative number. It's like negative a zillion, zillion, million, cajillion, umpteen million Googleplex, right? So -1 with 99 zeros coming after it, right? So that's as close to negative infinity as our calculator could possibly get. And that's going to be our leftmost bound. So, normal CDF, -1 e to the 99. Any less than or equal to problem, this is always what's going to be your lower bound, that -1 e to the 999. The upper bound is 2600, the mean's 3000, standard deviation is 250. Verify this, but when you plug all that into your calculator, you get roughly 5%. Okay, next type of problem. What's the probability that x is greater than or equal to some number b? So for example, I might ask, what's the probability that a walrus weighs greater than or equal to, more than or equal to, 2,900 pounds? Symbolically, this is the probability that x is greater than or equal to 2,900 pounds, or 2,900 pounds. So again, Appia buff. There's our picture. Make sure you understand where that picture is coming from. It's centered at 3,000. 2,900 is a little bit to the left, a little bit less than that. And we want everything more than 2,900, so I colored in, I shaded all the area to the right of it. Now, in this example, it's the lower or leftmost bound that's clear-cut. That's fairly obvious, hopefully, 2,900. What's unclear is the rightmost bound, because in theory there is no rightmost bound. In theory, that area just tapers off towards infinity, right? It goes forever in the rightmost direction. If I could, I would put an infinity for my upper bound, but there is no infinity button on my calculator. So I do the largest possible number that my calculator can handle. That's +1 e to the 999. It's saying take 1 and put 99 zeros after it. That's 1 quadrillion. That's an awfully big number. The mean is 3,000. The standard deviation is 250. Lower bound is 2,900. The upper bound is, there really is no upper bound, but we put 1e99, 3,250. You need to be able to do that. You need to be able to know how to type that into your calculator. Anytime I'm asking you for a greater than or equal to on a normal probability, you're going to put that 1e99 for your upper value. And so in this example, if I put all that into my calculator, I get 0.6554. So it's about 65.5% chance that that a walrus will weigh more than 2,900 pounds. Alright. So I mean, in theory, you should be prepared for doing lots of practice problems. I told you the 3 different types of problems, and we've done an example of each. Now, it's up to you, right? I can only show you. For you to actually learn it, you have to do lots of examples of it. But before you do that, I want to tie up a few loose ends. The first loose end is this. For a normal distribution, actually this is true for any continuous distribution, the probability that a random variable equals some number is always 0. That is, the probability that x equals a for any number a is always 0 again. This is if x is normal. This is not true if it's binomial. We know that already. But if it's normal, it is true. For example, if I asked you, what's the probability that a walrus weighs 3,025 pounds, we would actually, it's kind of a weird mathematical fact, but we would say that probability is 0. You might say that it's weird to say that because they're probably all walruses that weigh that, and it's true. But it's maybe like one walrus out of like whatever, the entire world population of walruses, right? Most of the time when the scale says 3,025, remember, we're talking about the entire continuum. Most of that time when the scale says 3,025, it's doing a little bit of rounding. That is, when it says 3,025, the walrus's actual weight is 3,025 and be 0.000357 pounds. The probability that without any rounding, that a walrus weighs exactly 3,025, right? That exact number, specific, without any rounding, bullseye, 3,025, it's essentially virtually impossible to happen. So the mathematical fact for continuous random variables is the probability that a normal random variable equals anything is always 0. That's why, right, the types of questions that I ask for a normal random variable is always questions like what is the probability it's between two numbers, or less than a number, or more than a number. It's always over ranges or intervals of value, never an actual number. The implication of what I just said, that the probability a random variable obtains a single number being 0, that implies that less than and less than or equal to mean the same thing, and that greater than or equal to mean the same thing, which means I can be sort of sloppy. And I don't know, you may or may not have noticed, I probably have been somewhat sloppy as I've been narrating these PowerPoints. For a normal random variable, the probability that x is less than a is equal to the probability that it's less than or equal to a, right? Those probabilities only differ because one includes a and one doesn't. But we know a itself, right? We know any particular number has 0 probability, doesn't contribute anything. Similarly, the probability x is greater than b is the probability x is greater than or equal to b. Right, so making it a little less abstract, the probability that x is more than 30 is the same as the probability it's greater than or equal to 30, right? Whether or not you have that equal sign there, it doesn't really matter. So you can be sort of sloppy about whether you put it there, don't put it there. It doesn't really matter. Again, this is only for continuous random variables, more specifically normal random variables. This is not a true statement for the binomial random variable. Now, two more things for us to talk about to kind of round out this normal random variable, and then we'll go ahead and we'll call it a PowerPoint. The first of the two things that I want to talk about are percentiles. We can use our calculators to very easily find percentiles for a given normal distribution. The arbitrary pth percentile of a normal distribution, it's defined as the value such that p% of the area of that curve lies to the left of it. For example, the 40th percentile of a normal distribution is the value such that 40% of the area lies to the left of it. We've talked about percentiles before in terms of Chapter 2, right? We said the median's the 50th percentile, right? The lower, or the first quartile, we said that's the 25th percentile, right? And the upper quartile, or the third quartile, is the 75th percentile. So, right, this concept of percentiles is not new to us. How do we do percentiles in our calculator? Well, it's going to be the same menu that we've gotten used to. Second, vars, and I think right below normal CDF, there's an inverse norm function. It's inverse norm. They call it inverse norm because it's sort of like the opposite or the reverse of our usual problem. Our usual problem is I give you like an X score, like a weight, and you give me the probability. Here I'm sort of giving you the probability and asking you to find the X score or the weight. So it's inverse norm, percentile, mean, standard deviation. This is one of those ones I never came up with a catchy little acronym for. We had NPR, our favorite radio station. We have LUMS, Lahore University of Managerial Sciences. I've never been able to come up with a good one. You have to come up with your own way of remembering this, but it's inverse norm, PMS. So, for example, what is the 40th percentile of walrus weight? Well, that's going to be inverse norm. So I put my percentile in. I believe I have to do the percentile as a decimal. So do it as 0.40. then the mean is 3,000, like it's always been. The standard deviation is 250. If we type that in there, verify this, you should get on your calculator 2,936.66. This means that 40% of all walruses weigh less than 2,936.66 pounds. That's what it means to be the 40th percentile. Alternatively, right, I could look at it a slightly different way. I could say, well, the area to the right, the percent of walruses that weigh more than 2,936.66 pounds is 1 minus 40%, or 60%. All right. Last topic of discussion. Let Z be the number of standard deviations an observation is above or below the mean. Again, this is something that we talked about at the end of Chapter 2. Hopefully you reviewed that before you went on to the section of normal random variables. It turns out that if the original observations X, say the weight of walruses, follow a normal distribution, then if you convert those to units of standard deviations, if you convert those to z-scores, those z-scores, it turns out, will also follow a normal distribution. So, the z distribution is a special type of normal random variable. It's a normal random variable with a mean of 0, right? Because, right, if something is right at the mean, its z-score is 0. Its distance from the mean is 0. And a standard deviation of 1, because, right, 1 indicates 1 standard deviation from the mean. It, by definition, the z distribution, by definition, by the way it's constructed, it deals with the number of standard deviations that an observation is above or below the mean. Understanding this is important for chapters 5 and 6. We're not going to use this, really, until chapters 5 or 6. But since it's a type of normal random variable, it's worth discussing and learning right now. So an example. Well, we already know this. We know that the probability a walrus weighs between 2,700 pounds and 3,300 pounds is given by, right, written symbolically, it's the probability that X is between 2,700 and 3,300. We know by now, this was in our previous PowerPoint, we could find that by doing normal CDF, 2,700, 3,300, the mean's 3,000, the standard deviation is 250. Now there's an alternative way that we could solve this, and you might say, why do I need a second way of doing this when I have one way that works just fine? It's a good question. The second way of being able to do it is going to become very useful to us, as I said, in chapters 5 or 6. So let's learn how to do it now. We can solve the same problem by taking the 2,700 and the 3,300 and figuring out what their z-scores are. Again, this is something we learned how to do at the end of Chapter 2. We do that by just basically subtracting the mean and dividing by the standard deviation. So if we do that, 2,700 minus 3,000 divided by 250. Put it in your calculator, you get negative 1.2. That's saying that a walrus who weighs 2,700 pounds is 1.2 standard deviations below the average walrus weight. If you do 3,300 minus 3,000, that thing divided by 250, you get positive 1.2. It's saying that, right, a walrus who weighs 3,300 pounds weighs 1.2 standard deviations above the mean or more than the mean. Now, if we're no longer dealing in units of pounds, if we're dealing with units of standard deviation, we no longer use X, we use Z. So what I am saying is that asking whether or not, or asking what the probability is that a walrus weighs between 2,700 and 3,300 is the same thing as asking what's the probability that a walrus weighs within 1.2 standard deviations of the mean. And we can solve that in our calculator by asking normal CDF. Our lower bound is negative 1.2. Our upper bound is 1.2. Our mean is 0. Remember, the mean of a z is always 0, and our standard deviation is 1. The standard deviation of a z is always 1. Right? So all I'm saying is that an alternative way of asking the question, what's the probability a walrus weighs between 2,700 and 3,300 pounds, is the same as asking what's the probability that its weight is within 1.2 standard deviations of the mean. So there are some practice problems that involve a z distribution. Anytime you see a z distribution, just think, okay, this is a normal random variable with a mean of 0 and a standard deviation of 1. So at the end of my little calculator function, I'm going to plug in 0, 1. And remember, I'm going to hit the next slide. I think this is the end of it. Remember, practice makes perfect. If there's one skill set from this class that you're going to master, make this the one that you master.
Oh, all right. So I lied. Here's a bonus problem for us. What is the probability that a walrus weighs between 0.7 standard deviations below the mean and 1.4 standard deviations above the mean? Ah, man, I really botched. I really ruined my dramatic exit, didn't I? Ah, what else? So be it. This is the same as asking, right, in units of standard deviations. Remember, z is just a placeholder for units of standard deviations. Symbolically, this is the same as asking what's the probability that negative 0.7, or z is between negative 0.7 and positive 1.4. Now, there should be a little bit of intuition on why we might approach a problem this way, right? We've talked in previous chapters that to statisticians, to researchers, it's really the standard deviation that is our natural measuring stick. That is, people who apply statistics tend to work not in units of pounds or inches or dollars, they tend to work in units of standard deviations. So it's very natural to approach a problem in this particular way. Again, remember, when we're talking about walruses, if I were to tell you that that a walrus weighs 4,250 pounds, and you don't have the context, which many of us don't, you wouldn't know what to make of that. You wouldn't know, is that a hefty walrus? Is that a scrawny walrus? I don't know. But if I told you that a walrus has a z-score of 5, if I told you that a walrus has a weight that's 5 standard deviations above the mean, and you're someone who understands statistics, then what would you do? Yeah, you would gasp. You would be flabbergasted. You would say OMG. You would say, oh my goodness, this is crazy. This is wow. This is a once in a lifetime walrus. So it is natural to try to approach problems this way, and this is how we would set that up. Now, to see the actual picture and the actual calculation, let's take a look at the next couple slides.
Well, again, Appia buff. Z is just the normal distribution, but remember, it's centered at 0. So I put that little line down the middle and I put 0. I want the probability that's in between negative 0.7, so that's my leftmost or lower bound, and 1.4, that's my upper or rightmost bound. So again, it's a normal probability. I solve it with normal CDF. LUMS, Lahore University of Managerial Sciences. Not a lot of people know this, but the greatest number of Nobel Prize winners, yeah, true fact, actually comes from the Lahore University of Managerial Sciences in scenic upstate Pakistan. So, my leftmost bound is negative 0.7. My upper bound is 1.4. The mean for a z, when we're talking about units of standard deviations, the mean is always 0 and the standard deviation is always 1. Verify that if you put all that in your calculator, you get 0.6773, and dang, you're getting darn good at doing this. That said, remember to do more problems and become even better still. Oh, and there we go. Practice makes perfect. I couldn't agree with myself more.